Everyone, Mr. Gustin here, at home with Grace, battling COVID. We're doing fine, but I wanted to touch base on a new concept for equilibrium. So we've studied equilibrium kind of conceptually, but we haven't studied it mathematically yet. So that's what we're going to do. And I'm over here in the slides for, it's called KEQ, and I believe the slides are from April 25th, 2022. So you can jump over there. It's slide 82 if you're in my class during the 2022 school year. So we're over there. We're on slide 84. Let's talk about this. Before we go ahead and dive into it, let's review. If this is my equilibrium, this is an example equilibrium, I would write the rate law. We talked about rate laws last unit in rates, and here it is. I would take the reactants, raise them to proper coefficients, which I would use data to calculate, and that would be multiplied by my rate constant, and give me the rate for that reaction. This unit, though, we're talking about equilibrium, where there's a forward reaction and a reverse reaction. So let's go ahead and also write the rate law for the reverse reaction. We would say that the rate of this reaction is equal to K for the reverse. We can call this for the forward, times the concentration of C raised to its exponent times the concentration of D raised to its exponent. Now, with equilibrium, the definition of equilibrium is that the rate forward is equal to the rate reversed. And if that's true, if the rates are equal when they're at equilibrium, we can actually kind of rework this equation and say that the K of the forward reaction times A to the A, B to the B is equal to the rate of the reverse reaction. This is true when we're at equilibrium. It's the definition of equilibrium. So if I start rearranging this and I bring my equilibrium constants to one side, I would divide this side by like K reversed, have them cross out. I would divide both sides by that, by K reverse. And I would also divide both sides by A to the A, B to the B. I'm left with this K forward over K reverse, which is equal to concentration of C D over the concentration of A to the A and the concentration of B to the B. Now this ratio, this K forward over K reverse, has a special name, and we call it KEQ. You all can hear Grace in the background probably. But this is a new expression. This is what's known as a K equilibrium or an equilibrium constant, and this is where we're going. Okay, this is where we're going with KEQ. Now, there are some notes in the slides that I want you to read about when the products are favored, when the reactants are favored, what this ratio will look like. But this is essentially what a KEQ is and where it comes from. Now, if we move on to the next slide, what we'll see is that what we already know, right? We know that equilibria can be shifted if I change concentration, pressure, or temperature. So when I'm writing my KEQ expression, I only need to include chemicals that will affect concentration, pressure, or temperature. And the only states of matter that affect those things are gases and aqueous solutions. So in a reaction, if there is a solid or liquid, it doesn't belong in my KEQ. I won't even write it. Go ahead to slide 86, and it shows you what I'm talking about. The KEQ for that expression is C cubed over B. Why? Because C and B are aqueous and gaseous, while A and D are both either solids or liquids. We don't include those in our KEQs because they do not affect the rate of the chemical reaction. Okay, this is pretty straightforward. I'm going to ask you to go through over on Canvas and work through some of the practice problems over there where there are explanations on how to write a KEQ, how to plug in numbers. There's a worksheet and a key there for you. I hope it makes sense. If not, I'm available. Email me, send me a reminder, whatever you need to do. I'm here for you. Okay? Good luck. I'll see y'all soon.